Okay, so we're starting out by defining the reference number, and it's in reference to what? Well, it's in reference to your position on the unit circle after traveling a distance t, either clockwise or counterclockwise. So if t is a negative number, then that means go clockwise. If t is a positive number, it means go counterclockwise. So the reference number, which is denoted t with a bar over the top, is the shortest distance along the circumference and it's always a positive number because this is a distance, right? To, I guess I should say from, yeah, I'm using the eraser. How about that? From P to the x-axis. All right, I guess we better have an example of that, huh? So let's draw a circle and maybe a few circles, right? So plot the center point for my circles. Okay, and should we have an x-axis? Sure, I think we can use the same line for both of them. And a y-axis here and a y-axis here. So this is the starting point. I never said from where, did I? Let's go back to our definition here. If t is the distance traveled around the circumference of the unit circle, I should say from 1, 0, right? That's our starting point to a terminal point P. Okay, so we start here. So in the text, should we go quickly to the text? They say the reference number, okay. And their definition, let t be a real number. The reference number t bar associated with t is the shortest distance along the circle between the terminal point determined by t and the x-axis. Okay, mine was a little bit more long-winded. Here's the algorithm, right? How to find the reference. Well, actually, here, using reference numbers to find terminal points, right? Okay, so if t is, say, 7 pi over 4, or 5, let's take 5 pi over 6. That's the first one they have there. Okay, so suppose that t is 5 pi over 6. Okay, so that's a multiple of pi, right? Is that a real number? Sure, pi is a real number, so 5 pi is a real number, and 1/6 of a real number is a real number. This is like, you could approximate this as a decimal, right? So why is it written as, you know, some multiple of pi over 6? Well, you know, here's pi over 2, right? That's the North Pole. That's 1/4 of the way around the circle. The whole way around the circle, you know, you're starting here, and when you go once around the units, this is the unit circle, right? So it's a circle of radius 1. We said last week that the definition of pi is the ratio of circumference to diameter. Shall we have a quick reminder about that? So here's another definition. Pi is the ratio of circumference to diameter on any circle, right? So that says that multiply both sides by d and swap the sides to solve for c. You get c is equal to pi d, but d is equal to 2r, right? So putting the numerical coefficient first, that comes out to 2 pi r, right? And if r is 1, then the circumference is 2 pi. So that's the distance around the unit circle. So we divide that into convenient chunks, right? So if the whole distance around is 2 pi, then half the distance around is pi. So this would be the terminal point for t equals pi. And a quarter is pi over 2, half a pi. This is 3/4 is 3 pi over 2. 3/4 of 2 pi. So where's pi over 6? Well, that's 1/3 of the way to pi over 2. So we divide this into 3 perfectly evenly spaced pieces. And 1/3 of pi over 2 is pi over 6. And 2/6 or 1/3 of pi is here. So this is pi over 3 or 2 pi over 6, if you like. Okay, and we can keep going by those. So, make steady hash marks of pi over 6 increments, right? 1 pi over 6, 2 pi over 6, 3 pi over 6 is pi over 2, 4 pi over 6, and 5 pi over 6 are going to be here and here. So 4 pi over 6 reduces to 2 pi over 3, huh? That's the same as 4 pi over. So we're counting by pi over 6. Pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, and reducing, right? So 5 pi over 6 doesn't reduce, and that's going to be right here. That's our terminal point, P, right? If we go a distance pi over 6 around the unit circle, that's where we're going to end up. So what's T bar then? For 5 pi over 6. And that's this distance here, right? The shortest distance along the circle. What is that distance? Well, this is 6 pi over 6, and that's 5 pi over 6. So the difference between those is pi over 6. The shortest distance, and it's always a positive number, right? Because it's a distance. So even if you're going clockwise that distance, the reference number is a positive number. Okay. They've got another one here. 7 pi over 4. Should we do that one? So 7 pi over 4, that's going to be over here. So let me show you how we get there. So here's 0, right? That's our starting point. That's 0 distance from here is what I mean, right? Obviously, this is the point. X coordinate is 1, the Y coordinate is 0, right? But so that's a distance 0 from that point. It is that point. Okay, so here's our reference. So what's the reference number for pi over 2? Well, it's equidistant from the left to the right. So either way, your distance of pi over 2 from the x-axis, right? If you're at pi, the reference number is 0, right? And 3 pi over 2, the reference number is again pi over 2. So where's pi over 4? Well, that's halfway between 0 and pi over 2, right? Let's say right about there. And then we can also count by pi over 4 around the circle, right? 1 pi over 4, 2 pi over 4 is pi over 2, 3 pi over 4 is going to be here, 4 pi over 4 is pi, 5 pi over 4 is in the third quadrant, 6 pi over 4 is coincident with 3 pi over 2, same point, right? Same number. And this is then pi over 4 more than 6 pi over 4, which is 7 pi over 4, and that's almost 2 pi, right? another, so what's the reference number? Well, that's this distance here. And T bar for 7 pi over 4 is pi over 4. So notice that T bar, so for all T, T bar is in the interval from 0 to pi over 2. It's never less than 0. It could be 0 if you're on the x-axis, but it can't be bigger than pi over 2. On the unit circle, you never a distance greater than pi over 2 from the x-axis. Along the circle, right? I'm not talking about the distance straight down, but the distance along the circle. Is that good? How are we doing? All right. So that's T bar. So let's look at the text a little bit more. They got another one here. This is hard to read. It's so small. Let me see if I can make it bigger. Get rid of this and zoom in. There we go. So here they have T is negative 2 pi over 3. And I won't write this on my paper. You can see it here well enough, right? So that means going clockwise 2 pi over 3. And, you know, that's the same as 4 pi over 6, right? So if we're talking about those pi over 6 measures, 3 pi over 6 is pi over 2 or negative pi over 2, right? Would be straight down. And then another pi over 6 gets you to 4 pi over 6 or 2 pi over 3 in reduced form. And of course, the negative means clockwise. So if T is negative 2 pi over 3, then your distance, you have to go another pi over 3 to get to negative 3 pi over 3, which is a point on the x-axis. And that's the shortest distance along the circle to the axis. So why are these important? Well, we use them to find terminal points. So here's the 1, 2, 3 procedure. So to find a terminal point P determined by any value of T, we use the following steps. Find the reference number, find the terminal point Q in the first quadrant determined by T bar, right? And that is going to be in the first quadrant because we've said that T bar is always a number between 0 and pi over 2. So then you just have to figure out which quadrant you're in, right? Which quadrant the point P is in. So you find the point Q referring to the reference point, and that has the same absolute value x, y coordinates as the point P. You just have to determine which quadrant P is in, right? So if you're in the first quadrant, both x and y are positive. If you're in the second quadrant, x is negative, but y is positive. Third quadrant, both x and y are negative. And fourth quadrant, x is positive, but y is negative. Okay, so they have a few examples, and we've done some. So how about 29 pi over 6? What's going on there? Well, there you want to find the, you know, this is more than a rotation, right? It's bigger than 2 pi. In fact, it's bigger than 4 pi, right? Because 29 is, well, let's see. So I guess we could say 29 is 24 plus 5, and 24 pi over 6 is 4 pi. And so you pull out the multiple of 2 pi, which in this case is 4 pi, or 24 pi over 6. And what's left over, it's kind of like long division, right? You're seeing what's left over after you keep subtracting 2 pi. And you can subtract 2 pi twice from 29 pi over 6, and the remainder is 5 pi over 6. So 5 pi over 6 has a terminal point in the second quadrant whose reference number is pi over 6. I think that was the first example we did, right? And we know that x and y for pi over 6, do we know those? Kind of, huh? Let's talk about that. So let's make another circle. Should I pull out my lead a little bit here? Oh, so round. Okay, I'm going to draw the x-axis through the center. And the y-axis perpendicular to that through the center. And this is the point 1, 0. And if we go pi over 6, that's 1/3 of the way to pi over 2, right? Those look like perfectly evenly spaced hash marks, marking off 1/3 the circumference for each. Then I'm going to do the same in the opposite direction. Yeah, perfectly evenly spaced. So I'm then going to join these guys. Okay, so this is pi over 6, and this is negative pi over 6. And these are radius lines, right? So I got a little triangle here, right? OPQ. So what kind of a triangle is OPQ? Well, what was our argument for this? I contend that the terminal point here is square root of 3 over 2, 1/2. And the terminal point here is square root of, it's the same x coordinate, right? But the y coordinate is negative 1/2. And these are both length 1. And so this is 1/2 up and this is 1/2 down. So this is also 1, right? So that's an equilateral triangle. Yeah, I mean, he's kind of using a circular argument here. I'm saying because this is 1/2 and this is negative 1/2, that's 1, and so it's the same as the radius. Well, if I think about, what point on the circle has a y coordinate of 1/2, that's going to be where you have the equilateral triangle, right? And that's not a really good argument, is it? I think we'll have to wait for a more solid argument, yeah. So the terminal point associated with pi over 6 is square root of 3. And how do we get that, right? Well, that's Pythagoras' theorem, right? So we have a little right triangle here. Can we, so these two angles are equal, right? And they have equal arcs, right? So they must be equal. And I have that just freehanding this triangle here, that if this is 1/2 and this is 1, then this is x. That's by Pythagoras' theorem. Which I'll just refer to as Pythagoras possessive. The sum of the squares of the legs. Sorry, the sum of the squares of the legs. Yeah, eraser. Is equal to the square and the hypotenuse. And so that says that x squared plus 1/4 is equal to 1, right? And then so x squared is equal to 1, take away 1/4, you got 3/4. And what's the square root of 3/4? Well, let's give ourselves a little space here. X could be plus or minus the square root of 3/4, but we're obviously here in the either quadrants 1 or 4 where x is positive. So I'm going to take the positive square root of 3/4, and I'm going to say that the square root of a ratio is the ratio of square roots. So on the top I have the square root of 3. At the bottom I have the square root of 4, but that simplifies to 2, right? So that's how we get the square root of 3/2. Okay, and so that's the terminal point associated with pi/6. How about 5pi/6? Well, that's has a reference number of pi/6. So if we follow that algorithm, let's do that. Okay, we've got a fresh sheet of paper. We need a fresh circle. So what we want to do here is find I'm going to need to sharpen that. So here's 1, 0 on the x-axis. And if t equals 5pi/6, then t bar is equal to pi/6, right? We saw that before, so we can mark off the circumference into thirds, trying to make perfectly evenly spaced hash marks and failing here. Okay. So here's 5pi/6. You can see that this distance is then pi/6, and pi/6 is over here, huh? Where the terminal point has coordinates square root of 3/2, comma 1/2. And so if this is P, then this is Q in the first quadrant. Oh, sorry, I should be using Q here then, right? The terminal point for the reference number has these coordinates. And we know that in quadrant 2, x is negative and y is positive. So we take the coordinates of the terminal point for Q and say, yeah, x is negative and y is positive. So just assign the appropriate signs, right? Is that sensible? And, you know, I'm kind of drawing it out here, but it should go more quickly when you get good at it, right? So here in example 7, I guess, right? Where they had a distance around the circle 29 pi over 6, which is equivalent to 2 rotations, right? 4 pi is 2 rotations, and then another 5 pi over 6. You end up over here. Let's see, over here. Okay. I don't know if you're seeing that. Yeah, you're not. Huh. How do I make my mouse visible? I don't know. I mean, it's visible on my screen, but I can see that it's not visible on your screen. Yeah, okay. Well, maybe it is visible now. I don't know. No, I guess it's not. Huh. Yeah, I'm trying to point at that 5 pi over 6, but okay. Where the reference point is pi over 6, we get the coordinates of pi over 6, and we see that at P, it's going to have the same absolute value for X and Y, but X is negative. All right. So back in the text, wow, okay. I guess we're ready for some exercises. This is odd. Okay. Yeah, it keeps, it's got some kind of, something's off here, huh? Yeah, notice the bottom of the screen is not scrolling, only the top of the screen. That's just bizarre. All right, let me see if I can fix that. Huh, how strange. Well, let's just ignore it, huh? Maybe if I do this, oh, here, and then, wow. So I get, maybe I have to crop that up, huh? Okay, that seems to have fixed it, huh? Okay. Nope. Mercy, what is going on here? I don't know. When it comes to Adobe, and maybe if I do this and then do this. Nope. At least one signature has problems. So maybe it's because I have a signature panel open. I don't want a signature panel open. That's Adobe for you. Okay, I'll tell you what we'll do. We'll open it in Sumatra and then use Sumatra instead, because that's just too distracting, huh? Okay, I have to find it then. Hello, Sumatra. Sumatra is just a PDF viewer. I'm going to say open, and I want to be in this thing here, and pre-calculus. Is this the right edition? I guess it is, huh? Yeah. So now I have to do a Sumatra thing here. Does this work? Okay. Yeah. Right. Okay. So much for Adobe, huh? Figures. Too many bells and whistles, I think, is their problem. So if I go to here, I guess I want to trim this up a bit so it fits in the proper window. And then get rid of that and zoom in, huh? I All right, sorry about all that. So we're getting to the exercises in the text. Oh, those are 5.2 exercises. I skipped right over them, huh? Here, okay. Yeah, this is, okay, here we go. Concepts. Okay, and is that too small? Let's zoom in a little bit further, huh? Let's use the scroll bar to go back and forth. So show that the point is on the unit circle. Oh, here's a good one, negative 24/25 and negative 7/25. And where on the unit circle would that be? So this is number 4. So here's what we'll do. So this is 5.1, number 4. Show that the point and the coordinates of the point are negative 24/25. That's pretty close to -1, huh? That's the x coordinate. So we're back over here somewhere. And negative 7/25 is a point on the unit circle. Well, let's locate it first, right? It's in the 4th quadrant. Both coordinates are negative. Can we write them as decimals? Would that make it easier? So negative 24/25, negative 7/25. We can multiply each one by 4/4, and you'll get negative 0.96, right? Because this will be 96/100 negative, and negative 0.28 as decimals, right? Again, 4/4, right? So you have 28/100, which is written as a decimal like that, right? And so let's find the y coordinate first, huh? I'm going to try to divide that into 10 equal parts, huh? Good luck. I suppose we can say it's about 3.2 centimeters, so about 1.6 is the halfway point. And then we can divide that into 5 equal parts, perfectly evenly spaced parts. So those are tenths, okay? And this is -1 down here on the y-intercept, right? So negative 2.8. Well, that's going to be pretty close to negative 0.3. So just a little bit above there. So I'm going to say, yeah, follow that over. And then, no, maybe even a little bit below there, huh? Yeah. Can I erase that? I know I'm making too much of a fuss about this. And then follow this up. And I was pretty close about the x coordinate there. It's actually even a little closer, 0.96, right? So that's less than half a tenth away from -1, right? Which is there. So we're here on the unit circle, right? So it looks like it's, at least approximately on the unit circle. How can we be sure that it's on the unit circle? Well, we can take those numbers and square them, right? So here's the governing equation for the unit circle in terms of x and y, right? The distance from the origin is 1 unit. The square of the distance is x squared plus y squared. And we can also draw in the hypotenuse of this right triangle here. Something like that. That's a distance of 1. So this edge is has length 0.96 or 24/25, and this edge has length 0.28. And I suppose we could square the decimals. Let's go ahead and square the fractions, right? So negative 24/25 quantity squared plus negative 7/25 quantity squared. That should be 1, right? So that's a question mark. Is that true? If it's true, then that's a point on the unit circle. So 24 squared is 576. 25 squared is 625, and the square of a negative is positive. So we get that fraction. And then 7 squared is 49 over 625. Is that equal to 1? If so, we got a point on the unit circle. And sure enough, these add up to 625. Do you see that? 9 and 6 is 15. Put down the 5, carry the 1, 4, and 7 is 11, plus the carry is 2, and then carry to get 625 over 625. And yes, that's 1. So yes, that's a point on the unit circle. And that points out, Pythagorean triples. So, you may get familiar with these. It's always a good idea to know a few Pythagorean triples, especially the simple little ones. So they include, 3 squared plus 4 squared equals 5 squared. So that's equivalent to saying 3/5 squared plus 4/5 squared is 1, right? Divide both sides by 5 squared. And so 3/5, 4/5 is a point on the unit circle. Where is it? I don't know. It's up here somewhere. 3/5 is about 0.6. So I think it's going to be right about there. Oh, right about there, I was saying. Here's the halfway point. Divide that into 5 equal parts. Divide this into 5 equal parts. So, okay, so 0.6 is actually closer to here. And so this would be 0.6, 0.8, huh? Or 3/5 and 4/5. Yet another location on the unit circle. Another Pythagorean triple. 5 squared plus 12 squared is 13 squared. All right, so that says that 5/13 squared plus 12/13 squared is equal to 1, right? And so there's 2. One other one. 8 squared plus 15 squared is 17 squared. That's a good one. Is that true? 64 plus 225 is 289, and that's the square of 17. So that says that, 8/17 squared plus 15/17 squared is equal to 1. And that's so this it could be either x is 8/17 and y is 15/17, or you could switch those around. X could be 15/17 and y could be 8/17, and you get a point, or they could all be either positive or negative, right? So in fact, it's like a house of mirrors. It's often an analogy I use for the unit circle. So I don't know, what is 8/17 as a decimal? Approximately? I'm going to use a calculator. Excuse me while I use a calculator. So where's my calculator? 8 divided by 17 on a Monday. Well, that's approximately, it's a little less than half, like 0.47. Okay. And 15 divided by 17. Oh, that's 18, isn't it? That's 0.88. Okay. So this is 0.47 approximately to the nearest hundredth, and 15/17 is approximately 0.88. How are we doing? It's coming up on the 13th hour. So if we were to plot those points on the unit circle, let's do it, huh? You know, I'm tempted to use a different unit of measure here. Can I do that? I need a fresh sheet of paper. But what I'm interested in doing is being able to mark off tenths conveniently. So for that purpose, I would like my radius to be, you know, something that, yeah, that ought to work, right? So now I've got 4 centimeters as my radius, a little bit larger. And here's the center point. So this should now be a diameter of 8 centimeters, huh? Pretty close. And this should also be a diameter of 8 centimeters. All diameters are congruent. And then we can mark off tenths. Is that true? So the halfway point, if this is 4, is going to be here. And what is that? That's 20 millimeters. Yeah, 2 centimeters is 20 millimeters. So every 2 hash marks, I'm going to have a tenth. Is that correct? Oh, actually, every 4 centimeters, I'm going to have a tenth, right? Because that's only half. So 4, 4, 4, 4, 4, 4, 4, 4, 4. And oh, I don't know. Do we care to do this over here? 4, 4, 4, 4, 4. I'm cutting off 4 millimeter hash marks. Okay, I can do the same thing on the vertical, right? And why am I fussing over all this? 8, 12, 16, 20, 24 millimeters, 28 millimeters, 32 millimeters, 36 millimeters, and going down 1, 2. These are perfectly evenly spaced hash marks, if I don't say so myself. Okay, so these are tenths, right? So if we have that, what were our numbers? 8/17 is approximately 0.47. So let's find that. So this is 1, 2, 3, 4, 5 is 0.5 is here. And this is 0.4 next to it. So 0.47 is going to be right about there. If I draw that going straight up from there, I'm going to get to a point now there. And 15/17 is about 0.88. And so if I draw this going over, that looks to be pretty convincing, huh? So this is a point on the circle where X is 8/17 and Y is 15/17. But we also have this point here, right? So if I go to 0.88 and follow that straight up, maybe about there. And I get to a place on the horizontal. Where's 0.5? Is that here? Yeah, we're at about 0.47, right? And as long as I'm doing that, I might as well go over to the other side, right? I can also follow this down. So here, this is what I mean by a house of mirrors, right? We got all these, and this I can follow over to the other side. And then follow this down. And try to make that perfectly vertical. And this should then be perfectly horizontal. And we can extend this to the other side. And what was it, 0.47? So yeah, right about there, huh? And then over here. So if we have 8 points then, right? You see them all? So this would be the point where x is 15/17 and y is 8/17. And here, x is 15/17, but y is -8/17. And here, x is 8/17, but y is -15/17. And over here, they're both negative, so -8/17. So you see the symmetry through the x and y axes. You've also got some symmetries through the origin, right? Here, if you reflect this point in the origin, you get to this point, right? Which is -15/17, -8/17. And then this point, we've got x is -15/17, but y is +8/17. And this point, we've got x is again negative, I say again, because same here, right? 17ths, but y is +15/17. And yeah, just from that one Pythagorean triple, we get these 8 points on the circle with nice rational coordinates. Okay. So what led me to do all that? Well, we were looking at a different Pythagorean triple. So we saw these Pythagorean triples. Are there any more? Yes, there are infinitely many Pythagorean triples. We saw this one, right? The 7, 24, 25. And there's actually a generator for these that we could talk about at some point. You just specify 2 parameters, m and n, and you get a way of generating infinitely many Pythagorean triples. Pythagorean meaning that you 3 integers such that the sum of the squares of the 2 smaller ones is the square of the larger one. All right, well, we better get on to the next section. We've got like 3 minutes to take a quick look at it. And I did want to broach that section today. Yeah, so we'll come back and look at these guys tomorrow, right? We're not done with section 1. There's more to talk about there. But yeah, so we've got trigonometric functions. Oh, sorry, Sumatra. Values of trigonometric functions and fundamental identities. So there's a lot in this section as well. A function is a rule that assigns to each real number another real number. Well, we knew that, right? So in this section, we use the properties of the unit circle from preceding section to define the trigonometric functions. Oh, how exciting, finally. So you can see that both x and y are functions of t. So let's go ahead and define x to be the cosine of t and y to be the sine of t. And I think maybe we'll go looking at, I don't know, this one. We've got these homework problems, right? And so with this one, let's tabulate, okay? So yeah, we have these. So I'm gonna, yeah, we don't really have time, do we? Got 2 minutes. So I'm going to attempt to spend too much time on that 17th problem, right? All right. So here's a unit circle. And I want to pick up the benchmark points, right? So these are not benchmark points per se. I mean, I suppose you could add them to your list of benchmark points, but we don't know what angle produces these, right? Sorry, what real number, what is t here, right? Hard to say, right? We don't know. But we do know that if t is pi over 4 or some multiple thereof, can I say this is the quarter way around the, or 1/8 of the way around the circle? And here's the perpendicular to that. And 1/3 is going to be, basically you divide this into thirds, but you only take the upper bit of that. So, and divide this into thirds and only take the lower bit of that. And then, okay, so I'm going to say we've got this. And, okay. This. Okay, so what are these? Well, this is pi over 6. This is pi over 4. This is pi over 3. And this is pi over 2. This is 2 pi over 3. This is 3 pi over 4. This is 5 pi. Are these getting to be familiar? This is pi. Here's 7 pi over 6. Here's 5 pi over 4. Here's 8 pi over 6, which reduces to 4 pi over 3, right? And this is 3 pi over 2. So 8 pi, 9 pi, 10 pi over 6 reduces to 5 pi over 3, 7 pi over 4. And this is pi over 6 shy of 12 pi over 6 is 11 pi over 6, huh? So those are the sort of solid benchmark points, I suppose, including 0, right? And if you make a table of values for t, the distance we're traveling, and x, or another one for t and y, we see that x is a function of t, and we'll take up from here tomorrow. And y is a function of t. And here's how we define this. This is how we define the trig functions, right? So definition, x equals cosine of t, which is abbreviated COS, and y is equal to sine of t. All right, well, at least we got those out of the bags. It's now 12:12, so we got to quit. I'll be in my office this afternoon if you care to drop by. The door's always open. And let me see if there's anything going on in the chat. Okay, no. Okay, any questions before we quit?
Where do I go to join you for the office hours? I've got some things I want to go over with you today.
Sure. Okay, so let me remind you of how to do that. So if we go, can we get rid of this and go to modules? Somewhere there's a module that says office hours. I think it's in week 2 or something. I just don't want to skip over it. Yeah, how to use office hours. It's in week 4, I guess. I moved it. We used to be in week 2. So these are the steps, right? So you go to the dashboard on Canvas, click on Confer Zoom, go to appointment booking. So that's sort of the crucial step, and click on Book an Appointment with and choose the name of your instructor. View available slots for the day or week. Change the view on the right-hand side. Book an appointment, filling in the info on topic and any details, and then click save, and then I'll see that you're waiting. All right. Okay.
Okay.
See you there.